As a result, it means that Ajit is smoking and we do not agree with Ajit. In this video, we'll solve the October-November 2023 question paper 62, Probability and Statistics 2 paper for the CIE A Level Maths 9709 exam board. Let's get into it. Number 1, Part A. The random variable x has the distribution Poisson with lambda 25. Use the normal approximation to the Poisson distribution to find the probability that x is greater than 30. Okay, so we have x follows a Poisson distribution with lambda 25. So this means that if we're now approximating to the normal distribution, x follows a normal distribution with lambda, since lambda is both mean and variance, we can say lambda. So x follows a normal distribution with mean 25 and variance 25, and we are required to find the probability that x is greater than 30. So remember that the Poisson distribution is a discrete distribution and the normal distribution is a continuous distribution. So it means 30 under a continuous distribution represents any value from 29.5 to 30.5. So we are saying we want greater than 30, so we don't want to include 30. So we want the probability that x is greater than 30.5. And now let's standardize. So probability that z is greater than 30.5 minus 25 over the square root of 25, and this is probability that z is greater than, let's punch that into a calculator, 30.5 minus 25 over root 25, which gives 1.1, and we can write this as 1 minus phi of 1.1. Read of phi of 1.1 from the tables, that gives 0.8643, which simplifies to give 0.136, and that's our final answer for part A. Let's move on to part B. A random variable y has the distribution binomial with n100 and probability of success p, where p is less than 0.05. Use the Poisson approximation to the binomial distribution to write down an expression in terms of p for the probability that y is less than 3. Okay, so we are given that y follows a binomial distribution 100 and p. If we come to the Poisson distribution, Poisson, lambda would be 100 times p, so lambda will be 100 p. And now we want to write down an expression in terms of p for the probability is less than 3. Okay, so that's the probability that y is less than 3, which is equal to the probability that y is equal to 0, 1, 2. We can write that as the probability that y is less than 3 is equal to e to the negative lambda, which is 100p, open brackets. So when y is 0, this will be 1. When y is 1, that will be 100p. And then when y is 2, that's 100p squared over 2 factorial. And so this would be our final answer. You can still simplify this further, but you can also leave it like this. Since they've just asked you to write down an expression, they've not asked it to be in its simplest terms. The length in minutes of mathematics lectures at a certain college is mean, mu, and standard deviation 8.3. Part A. The total length of a random sample of 85 lectures was 4,590 minutes. Calculate a 95% confidence interval for mu. Okay, so we want a 95% confidence interval for mu. The formula we're going to use is x bar plus or minus z times sigma over root n. So in this case, our x bar would be 4,590 minutes divided by the number of lectures. So that's 4,590 over 85 plus or minus, we need to evaluate Z. Sigma is 8.3 over root 85. So this is a 95% confidence interval. So it means this area in the middle would be 95%, and this area on the side would be 2.5% and 2.5%. So that means the Z value here is the Z value we're looking at. If you read your tables in reverse, you should get that the Z value is 1.96. So we substitute it here. That's 4,590 over 85 plus or minus 1.96 times 8.3 over root 85. Let's punch this into a calculator. So we've got 4,590 over 85 minus 1.96 times 8.3 over root 85, and that gives us 52.2. So therefore, we've got 52.2, and then the upper boundary would be 55.8. 55.8, and this would be our final answer. Let's move on to part B. The length in minutes of history lectures at a college's mean M and standard deviation is. Part B. Using a random sample of 100 history lectures, a 95% confidence interval for M was found to have width 2.8 minutes. Find the value of S. Okay, so the formula for interval width would be 2 times Z times sigma over root n. And in this case, we're told that our width is 2.8. Again, this is a 95% confidence interval, so our Z value is 1.96. So this is 2 times 1.96 times sigma. Sigma is S over root n. N is 100, so this is root 100 is equal to 2.8. Okay, so let's simplify the left-hand side first. So that's 2 times 1.96 divided by root 100, and that gives us 0.392. So this becomes 0.392. S is equal to 2.8. Divide both sides by 0.392. You get 2.8 divided by 0.392, which gives us 50 over 7. 50 over 7. And this would be our final answer. Let's move on to the next question. Number 3. A researcher read a magazine article which stated that boys aged 1 to 3 prefer green to orange. It claimed that when offered a green cube and an orange cube to play with, a boy is more likely to choose the green one. The researcher disagrees with this claim. She believes that boys of this age are equally likely to choose either color. In order to test her belief, the researcher carried out her hypothesis test at the 5% significance level. She offered a green cube and an orange cube to each of 10 randomly chosen boys aged 1 to 3 and recorded the number X of boys who chose the green cube. Out of the 10 boys, 8 boys chose the green cube. Part A, Part 1. Assuming that the researcher's belief that either color cube is equally likely to be chosen is valid, a student correctly calculates that the probability that x equals 8 is equal to 0.0439, correct to 3 significant figures. He says that because this value is less than 0.05, the null hypothesis should be rejected. Explain why the statement is incorrect. Because since it says that out of the 10 boys, 8 boys chose the green cube, our critical region will actually be x is greater than or equal to 8. The student has only considered x is equal to 8. So only when the probability that x is greater than or equal to 8 is less than 0.05, then can we conclude that we should reject the null hypothesis? So we can say that the student is supposed to evaluate or is supposed to calculate the probability that x is greater than or equal to 8, not the probability that x equals 8. Part 2. Carry out the test on the researcher's claim that either color cube is equally likely to be chosen. Okay, so let's start by defining our null and alternative hypothesis. H naught would be the probability. So we have a green cube and an orange cube. So the boy can either choose a green cube or an orange cube, which is a 1 in 2 chance of picking a green cube. So that's 0.5. And then H1, we are told that, let's go to the stem of the question. It claimed that when offered a green cube and an orange cube to play with, the boy is more likely to choose the green one. So this means that this is an upper tail test. They're saying that the probability of picking a green cube is greater than 0.5. So that would be our alternative hypothesis. So now, assuming that H naught is true, we can say that X follows a binomial distribution. There were 10 boys that were sampled, so that's 10. And since we're assuming that H naught is true, we can say that our probability of success is 0.5. And now we are testing, it's an upper tail test. Add the 5% significance level. We will reject H naught if the probability that X is greater than or equal to the critical value is in fact less than our significance level 0.05. So now we know that our critical value, as was given in the stem of the question, our critical value is 8. So we can evaluate that and check if it's less than 0.05. So the probability that X is greater than or equal to 8, that's equal to the probability that X is equal to 8, 9, or 10. The probability that X is equal to 8 was given here as 0.0439. So that will be 0.0439 plus 10 choose 9 times 0.5 to the power 9 times 0.5 to the power 1 plus 0.5 to the power 10. That's for when x is equal to 10. So the probability that x is greater than or equal to 8 is equal to, let's punch this into the calculator, 0.0439 plus 10 choose 9 times 0.5 to the power 9 times 0.5 plus 0.5 to the power 10, and that gives us 0.0546. So 0.0546 is greater than 0.05. As a result, it means that we are accepting H naught. Accept H naught. Since our rejection rules say that we're only going to reject H naught if the probability that X is greater than or equal to C is less than 0.05. In this case, it's greater than. So we're going to accept H naught. And now let's conclude in context. And we can say that there is not enough evidence. At the 5% significance level that a boy is more likely to pick a green cube over an orange cube and this would be our final answer. Let's move on to part B. Another researcher claims that a type 1 error was made in carrying out the test. Explain why this cannot be true. Okay, so a type 1 error is when you reject H0 when H0 is true. So if we go back to our hypothesis test, we accepted H0. So we cannot make the mistake of rejecting H0 when H0 is true, since we did not reject H0. So our answer would be it cannot be true because we did not reject H0. We did not reject H0. A similar test at the 5% significance level was carried out later using 10 other randomly chosen boys aged 1 to 3. Find the probability of a type 1 error. Okay, so from our earlier test, we said our rejection rule would be reject H0 if the probability that X is greater than or equal to C is less than 0.05. So now we don't know what the critical value is, and we need to find type 1 error. So a type 1 error, we're basically finding the probability of being in the critical region, the probability of being in the rejection region. So we need to find what our rejection region is. So to do that, we're going to use trial and error. So now let's start with when X is greater than 10. So the probability that X is greater than or equal to 10. So we actually did calculate this in an earlier part. That's 0.5 to the power 10. This is 0.5 to the power 10. Let's punch that into the calculator. 0.5 to the power 10. This is 0.000976. Let's put it to 4 significant figures, so 6. And we can tell that this is still less than our 0.05. So let's try again. X is greater than or equal to 9 is equal to, it will be this value, probability that X equals 10, and then the value for when X is equal to 9. So that's 10 choose 9 times 0.5 to the power 9 times 0.5 plus the 0.000976, and let's punch that in the calculator. 10 choose 9 times 0.5 to the power 9 times 0.5 plus 0.000976, and this gives us 0.01710742 and so on. Okay, then probability that X is greater than or equal to 8. I'm sure we calculated this earlier on in our test, and that gave us 0.0546. So this would be 0.0546. Now you notice that this value is actually bigger than our significance level. So that means that when we now look at 8 as the critical value, we're already out of the rejection region. That means only 9 and 10 are actually in the rejection region. As a result, our rejection region is X is greater than or equal to 9. So since the probability of a type 1 error is the probability of being in the critical region, we can say that the probability of a type 1 error is the probability that X is equal to is greater than or equal to 9, which we evaluated to be 0.0107 to 3 significant figures. And that will be our final answer. Number 4. The height h in meters of mature trees of a certain variety is normally distributed with standard deviation 0.6. In order to test whether the population mean of h is greater than 4.23, the heights of a random sample of 200 trees are measured. Write down suitable now and alternative hypothesis for the test. Okay, h0 and h1. So we are told that in order to test whether the population mean of h is greater than 4.23. So we're testing that mu is greater than 4.23. So this would be our alternative hypothesis. That means that our now hypothesis would be mu is equal to 4.23. Let's move on to the next part. The sample mean height h bar meters of the 200 trees is found and the test is carried out. The result of the test is to reject the null hypothesis at the 5% significance level. Part B. Find the set of possible values of h bar. Okay. So what we can do is sketch our bell curve. We know that our test is being carried out at the 5% significance level and it's an upper tail test. So it means that this region over here is 5%, meaning that that region over here is 95%. So if we go to our normal distribution tables, we know that our z value here will be 1.645. So we can create a rejection rule, which would be reject h0 if z is in the critical region, so that's if z is greater than 1.645, and our z is equal to the h bar here, which is the sample mean, h bar minus mu is 4.23 over our standard deviation. Our standard deviation is in the stem of the question, 0.67. And remember that this is sample mean, so it's actually sigma over root n. So 0.67 over the square root of n. N is 200. And so we can't really simplify this further. So let's go back to our rejection rule. It says reject h0 if z is greater than 1.645. And we found that our z is equal to h bar minus 4.23 over 0.67 divided by root 200. So this will become h bar minus 4.23 over 0.67 over root 200 is greater than 1.645. 1.645. Let's get rid of the denominator. H bar minus 4.23 is greater than. So this is 1.645 times 0.67 over the square root of 200. So that gives us 0.07793 to 4 significant figures. So h bar would be greater than 4.23 plus the 0.07793. H bar would be greater than, this is 4.23 plus 0.07793, and that gives us 4.31, correct to 3 significant figures, and this would be our final answer. Part C. Ajit said, in B we had to assume that h bar is normally distributed, so it was necessary to use the central limit theorem. Explain whether you agree with Ajit. Okay, so in part B, we used a sample mean, and our sample mean was based off of our population, H, which is normally distributed. And we know that if our population is normally distributed, then the sample mean is also normally distributed. which means that there is no need for us to use CLT since our sample mean is already normally distributed. As a result, it means that Ajit is smoking and we do not agree with Ajit. Therefore, we can conclude that no, we do not agree with Ajit. Agree with Ajit. The population H is normally distributed. Is normally distributed. And this would be our final answer. Number 5. The random variable x has probability density function f given by f of x is equal to 1 over x squared when x is between a and b and f of x equals 0 otherwise, where a and b are positive constants. It is given that the expectation of x is equal to ln 2. Show that b is equal to 2a. So we can use the formula for expectation of x, which is available in the MF19. So that's with the limits a and b, x times f of x, which is 1 over x squared, and this is with respect to x, and we know that this should be equal to ln 2. So we can simplify here, cancel out, you end up with the integral from a to b of 1 over x with respect to x, and it's equal to ln 2. If you integrate, you get ln x with the limits a and b should be equal to ln 2. Substitute in your limits, you get ln b minus ln a is equal to ln 2. And we can use laws of logarithms to combine this to be ln b over a is equal to ln 2, and apply the exponential function to both sides, and that becomes b over a is equal to 2, and let's make b the subject of the formula. You get b is equal to 2a, and that's our final answer. Part B, show that a is equal to 1 over 2. Okay, so what we can do here, we've been given that b, we've proved that b is equal to 2a, so we can say the integral from a to b, b is 2a of f of x, which is our function, f of x, which is 1 over x squared with respect to x. We know that if we integrate from the lower limit to the upper limit, we should get 1, since this is a probability density function. So this is the integral of a from a to 2a of x to the power minus 2 with respect to x, and we know that it should be equal to 1. If we integrate, we get negative 1 over x, and our limits are from a to 2a. We know that this is equal to 1. Let's substitute in our limits. This becomes negative 1 over 2a minus 1 over a, and this is equal to 1. So you get 1 over a minus 1 over 2a is equal to 1. If we put them under one common denominator, the common denominator is 2a. So this becomes 2 minus 1 is equal to 1. So you've got 1 over 2a is equal to 1, which then results in 2a is equal to 1. So a must be equal to 1 over 2. And that's our final answer. Part C, find the median of x. So the median is the middle value, so we can integrate from our lower limit, which is a, and we have proved that a is half, so we can integrate from half to the median, the middle value, and our function f of x is x to the power minus 2 with respect to x, and we know that since this is the median, it should be equal to half. So if we integrate, we get negative 1 over x. Our limits are half and m. This is equal to half. Substituting the limits, this becomes negative 1 over m minus 1 over half. This is equal to half. So this is negative 1 over m, and this should be plus 2 is equal to half. So this becomes negative 1 over m is equal to half minus 2, which is minus 3 over 2, and so let's cross multiply. This becomes negative 2 is equal to negative 3m, and so it means that m is equal to 2 over 3, and this would be our final answer. Number 6. A factory makes loaves of bread in batches. One batch of loaves contains X kilograms of dried yeast and Y kilograms of flour, where X and Y have independent distributions. The first one is the normal distribution with mean 0.7 and variance 0.02 squared, and the second one is the normal distribution with mean 100.0 and variance 3.0 squared. Dried yeast costs $13.50 per kilogram and flour costs $0.90 per kilogram. For making one batch of bread, the total of all other costs is $55. The factory sells each batch of bread for $200. Find the probability that the profit made on one randomly chosen batch of bread is greater than $40. So we're given that we have one batch contains X kilograms of dried yeast, and each kg of dried yeast costs 13.50 per kg. So we can say 13.50 times X, and flour costs $0.90 per kilogram. So we can say plus 0.90 Y. And then for making one batch of bread, the total of all other costs is $55, so plus 55. So what we have here are the total costs of making one batch of bread. So this is total costs. And now we are told that the factory sells each batch of bread at $200. And what we want is the profit. This is the selling price. Our profit is selling price minus cost price. So that simply becomes profit, let P equal 200 minus the 13.50x plus 0.90y plus 55. So this would be our profit. And we're told that our profit should be greater than, we want the probability that the profit is greater than 40. So in other words, this is the probability that P is greater than 40. So we can substitute this with P. We're looking for the probability that 200 minus, in brackets, 13.50x plus 0.90y plus 55. All of this represents P, and we want it to be greater than 40. So I'm going to move the 40 to the other side, so it becomes 200 minus 40, which would give us 160. Then I'm going to expand our bracket. That's minus 13.50x minus 0.90y minus 55. And this is now all greater than 0 since we've moved the 40 to the left-hand side. To make our lives simpler, we're going to rewrite this whole expression as W. So W is equal to 160 minus 13.50x minus 0.90y minus 55. So what we're looking for is the probability that W is greater than 0. So let's find our expectation for W. Our expectation will be 160 minus 13.50. The mean of X is 0.7. 0.7 minus 0.90 times the mean of Y is 100, and then minus the 55, minus 55. And so the expectation of W is equal to Let's punch this into our calculator. 160 minus 13.50 times 0.7 minus 0.90 times 100 minus 55, and that gives us 5.55. 5.55. And now let's find the variance of W. So var of W is equal to, this doesn't have a variance, it's a constant, so that would be 13.50 squared times the var of x. The var of x is 0.02 squared plus 0.90 squared times the variance of y. The variance of y is 3.0 squared. So this is 3.0 squared. The 55 doesn't have a variance since it's a constant. And now let's punch that into our calculator. So that's 13.50 squared times 0.02 squared plus 0.90 squared times 3.0 squared, and this gives us 7.3629. 7.3629. And so this means that W follows a normal distribution with mean 5.55 and variance 7.3629. And we said we're trying to solve probability that W is greater than 0. So now let's standardize. This is probability that Z is greater than 0 minus 5.55 over the square root of 7.3629. This is the probability that Z is greater than. Punch that into your calculator. That's negative 5.55 over the square root of 7.3629. And this gives us negative 2.045. Negative 2.045. And this would be phi of 2.045. Read this value off your normal distribution tables and you should get 0.9795, and this would be our final answer. Number 7. A random variable x has distribution Poisson with lambda 2.4. Part A. Find the probability that x is between 2 inclusive and 4. So we want the probability that x is equal to 2 and 3. So this is e to the power negative lambda, which is 2.4. And then that will be 2.4 to the power 2 over 2 factorial plus 2.4 to the power 3 over 3 factorial. And let's punch that into our calculator. So that's e to the power negative 2.4 open bracket 2.4 squared over 2 factorial plus 2.4 cubed over 3 factorial, and this gives us 0.470. 0.470, and this would be our final answer. Let's move on to part B. Two independent values of x are chosen. Find the probability that both of these values are greater than 1. Okay, so let's start by finding the probability that only one of these values is greater than 1. So that's the probability that x is greater than 1. And we can write that as 1 minus the probability that x is less than or equal to 1, which is 1 minus the probability that x is equal to 0 or 1. And we can write that as 1 minus e to the negative lambda. Lambda is 2.4, and that's 1 plus 2.4. And then this would be the probability of only one of these values being greater than 1. And now we want the probability of two of these values being greater than 1. So we simply square our answer. 1 minus e to the negative 2.4. 1 plus 2.4 squared. And that will give us our final answer. Let's punch that into the calculator. 1 minus e to the negative 2.4. Open bracket. 1 plus 2.4 squared. And that gives us 0.478. And that's our final answer. Let's move on to part C. It is given that the probability that x is equal to r is less than the probability that x is equal to r plus 1. Part 1. Find the set of possible values of r. Okay, so we can write the probability that x equals r as e to the negative lambda, which is 2.4, times lambda 2.4 to the power r over r factorial, and this is less than e to the negative 2.4 times 2.4 to the power r plus 1 divided by r plus 1 factorial. And you notice that we can simply divide both sides by e to the negative 2.4 and they cancel out. So what you end up with is 2.4 to the power r over r factorial is less than 2.4 to the power r plus 1. Using laws of indices, we can split that to become 2.4 to the power r times 2.4. And then our denominator r plus 1 factorial can be written as r factorial times r plus 1. So let me explain that. Say for example we've got 3 factorial. 3 factorial is equal to 1 times 2 times 3. And now let's do 3 plus 1 factorial. 3 plus 1 is 4. So that's 4 factorial. That's equal to 1 times 2 times 3 times 4. Notice how we can write our 4 factorial as this 1 times 2 times 3. We've said it's equal to 3 factorial. So we can write that as 3 factorial times 4. So that means r plus 1 factorial can be written as r factorial times r plus 1. And that's what we've simply done over here. And now we can cancel out like terms. You notice that on both sides we've got 2.4 to the power r, which is here on the left hand side and here on that side. And we've got r factorial on the denominator as well. So that will cancel out and you end up with 1 is less than 2.4 over r plus 1. So if we simplify this, r plus 1 is less than 2.4. I is less than 2.4 minus 1. I is less than, this is 1.4. Okay, so notice that the Poisson distribution is a discrete distribution, so it only takes discrete values. So it means r must be a discrete value, so r is representing a set of discrete values. So we want the discrete values that are less than 1.4, and those values are 0 and 1. So this would be our final answer. Part 2. Hence find the value of r for which the probability that x equals r is greatest. Okay, so we know that our values are r is equal to 0 and 1. And from part 1, we were given that the probability that x is equal to r is less than the probability that x is equal to r plus 1. So the probability that x is equal to r is less than the probability that x is equal to r plus 1. Now let's substitute. When r is 0, we get the probability that x is 0 is less than the probability that x is equal to r plus 1. So that's 0 plus 1 is 1. And then let's substitute. When r is 1, we get the probability that x is equal to 1 is less than the probability that x is equal to 1 plus 1, which is 2. And so now in this case, for the first one, we've got the probability that x is equal to 1 is greater than the probability that x is 0. So in this case, the greatest value for the probability that x is equal to r would be 1. But then we then go on with the probability that x equals 1, and when we compare it to the probability that x equals 2, we get that the probability that x is equal to 2 is in fact greater than the probability that x is equal to 1. So it must mean that the value of r, which yields the greatest probability that x is equal to r, is 2, and we can conclude that r is 2, and that's our final answer. And I believe that's the last question. Okay, so that's all for today's video. Thank you for watching. If you enjoyed the video, like and subscribe for more videos like this. Comment down below which paper would you like to see me break down next. Bye bye.